Hi, so this is the magnetic fields of a bar magnet video. So the purpose is to measure the distance dependence of the magnetic field due to a small bar magnet. And then we're going to compare the observed versus the predicted distances of the on-axis and off-axis magnetic fields, which will be derived from the Biot-Savart law. So we're going to be using GlowScript as our computational model, and the results we've gotten is n equals negative 2.89984, and the magnetic dipole moment is 4.616 nm3. So first we have Biot-Savart's law, which describes a magnetic field generated by constant electric current and relates the magnetic field to magnitude, direction, length, and proximity to electric current. And then we have the magnetic field of dipole, which is closed circulation of electric current system, and the distance dependence formula, which is the magnitude of magnetic field due to a bar magnet falls within distance. So then for the experiment, we're going to first position the phone so that the magnetometer is perpendicular to the Earth's magnetic field, then identify where the magnetometer chip is located on the phone, then measure the distance between the magnetometer and the bar magnet in both on-axis and off-axis positions. This is the data for the on-axis scenario. To the left, we have the distance measurements for different magnetic field strengths, and on the right, we have the linearized plot of the averages based on our distance dependency formula, and the equation of line best fit, so we can determine the variables n and k. And now that we know n and k, we can solve for the magnetic dipole moment mu, which is found to be 3.89 am squared. So then for the next scenario is the off-axis magnetic field. This process is similar to what we did for the on-axis, except now we have to move the magnetometer up and perpendicular to the direction of the x-axis, and the results for the x, y, and z components of the magnetic fields at a perpendicular distance of 0.196 m is given in the table. Now that we have the observed data out of the way, we can move on to the computational model. And the first step is to create a function for the magnetic fields and to set our initial conditions, particularly the magnetic dipole moment that we found in the previous steps. Here coded the visual aspect of the model. And then to do this, I specify the magnitude and direction of the two on-axis arrows, 4 perpendicular off-axis arrows, and 1 arrow 45 degrees from the axis. The predicted magnetic field is highlighted in blue, which is relatively similar to our observed model. Although there are some discrepancies in this lab, we had to make a few assumptions and had room for potential error. And then the main assumption that we made was that the bar magnet acted as magnetic dipole, and the main error was that other electronic and magnetic objects in the room skewed with the magnetometer data. So now for a deeper dive for the what if questions. What if we hadn't compensated for magnetic north and instead placed our meter stick at the intermediate angle relative to Earth's magnetic field? Well, the Earth's magnetic field would interfere with the bar magnets in the magnetic field, and this would skew the results. And then for the next one, we have what if connected two identical magnet ends to end and repeated all these experiments. Well, the magnetic field magnitude would double and the direction would stay the same. Thank you.